So, couple quick reminders. Remember, office hours coming up on this coming Monday. Canvas quiz closes on Friday, 5 p.m. And as a reminder, the Undergraduate Chemistry Society's faculty meet and greet is coming up Friday, March 6th. This is going to be a research info event at 3:30 in Chemistry D Wing 215. And then free food, 5 p.m. to 8 p.m. Faculty will be there to sort of, again, talk about, this is a good chance if you're interested in joining other labs or volunteering or learning more about what's happening. It's a great chance to connect into other point. Yeah, sorry, question.
Can I add in, it's $5 cash.
What's that?
$5 cash.
$5 cash only. Cool. All right. So, last class, we talked about the aldol condensation. This is the second step. We're not just making the bond, but we're using water extrusion to make a double bond. This is our alpha, beta, and saturated systems. We then started talking about the problems that come with these mixed or crossed aldols. If you don't have this single dimerization, you have all these different permutations of products that you can generate. We started talking about how we control that, so that's like obligate donors, obligate acceptors, concentration gradients as we add things in different orders. And then we introduced what's called the Canova-Nagel reaction. That's just an intramolecular version of the aldol condensation. This is where the donor and the acceptor are part of the same molecule at the same time. So, this is that practice going backwards. If this was your molecule, draw the starting materials, label the donor, label the acceptor if you tried to make this aldol condensation product. Walk backwards. Where did you start? Okay, let's try breaking this down. So in this question, we're telling you outright, this is the product of an aldol condensation. That's again, we're telegraphing a part of it. Now, if you're doing this one where it's like, just make this material, you don't know necessarily it's an aldol condensation, what are the features of this? What are the structures, functional groups that you are looking for to telegraph this came from an aldol condensation? What are you looking for? Yeah, you're looking for this alpha, beta, unsaturated system. That carbonyl skip double bond is a really strong tell. This came from an aldol condensation, somehow. When we do that, we're looking for the fragments that sort of make it up. That means I'm making this double bond. That's the core part of how this new carbon-carbon bond came together, right? That's where those two fragments came in. If I'm doing that, you could sort of take one of two strategies. Remember, if this is the double bond, that's where I'm fragmenting it. I have to break that in two species, and I have my donor and my acceptor. Remember, your donor is what? Your nucleophile or your electrophile? Donor is your nucleophile. That's the enolate part of it. And you can see donor. The donor is made up of whatever still has the carbonyl because it came from the enolate. The acceptor is the electrophile. So that way, this part would be my acceptor, my electrophilic fragment. This piece over here is my donor or my nucleophilic fragment. Again, nucleophile still contains the carbonyl. Electrophile contains what used to be the carbonyl. The double bond that you're targeting here, this carbon here, is the carbonyl. That's what used to be the carbonyl that was attacked by that electrophile, or by that nucleophile. That means this center here, either side, the two carbons either side of the bond that we're trying to fragment, that's where the business end is. The blue center, that's my enolate, my carbon minus. The pink center, that used to be the carbonyl. That's the electrophilic part. If you're working backwards one by one, you might say, all right, I'm just going to hydrate. I'm going to go from the condensation product back one step to the aldol addition product. So we're just adding water across this double bond. And when we do this, the water ends up attached to the electrophilic fragment. That's where you used to have a carbonyl. You've dropped it down to an sp3 when you do that. And then one step back from that, we're fragmenting this bond completely. That gets us the carbonyl fragment. And, oh, let's do my color coding correctly. Nucleophile would have been this fragment. That's my donor, where that carbon is that carbon, which is that carbon. And the electrophile would be simply this aldehyde. You're going back to that higher level. That carbon is that carbon, which is back to that carbon here. So that way, my donor is my blue guy. This is my nucleophile. My acceptor, it's my electrophile. Remember when we talked about this before, is this an obligate acceptor? If you look at that acceptor, is this something that can only be an acceptor, or are we going to have problems with different substitution patterns? Basically, can I make an enolate from my acceptor? No. No alpha protons. That's why we're choosing it. It's an aldehyde only. It's an electrophile only. That's why it's useful, because we can use this fragment. There's no problem about making sort of mixed aldols or mixed other components. This is a typical way we'd use this. Next one, quickly. If I took this material under these conditions, what's the product you generate? So we're going to go speed round. You have 1 minute to discuss amongst your people, and I'd like to hear your answer. Go.
Is this just a Claisen or? For this one, how do you differentiate between like a HW3 and a
I'll answer after class. I'll show you what I mean. I know what you're talking about. You're missing a carbon. Okay. So, you're starting off with this molecule. What functional group is most important in here? What functional group is reacting? This one here, what do we call this? That is a ester. If you take an ester, and you treat it with sodium hydroxide, that's a base. Heat and water, what's your product? It's a what functional group? It's a carboxylic acid. This is a saponification only. You're doing this, where your base is acting as a nucleophile. That's why I'm pulling this back, is again, now you're starting to see similar conditions being applied to molecules. This goes back to nucleophilic acyl substitution. This is our soap-making reaction. Strong base in water plus heat with an ester is going to punch out that ester to give you carboxylic acid. Why does it not deprotonate here? Like, yeah, it's a base, yeah, it's a carbonyl, but why not? Yeah, the pKs are not helping you out here. Remember, sodium hydroxide is the conjugate base of water. pKa are about 15, 14. The alpha protons of an ester are up towards 25. These are not super acidic. So you do not have, they're not acidic enough to deprotonate, so you're not making enolates. Since you're not making enolates, you can do deprotonation, or you can do nucleophilic attack of my hydroxide. Worse yet, this is what you'd get after workup. Under basic conditions, what does this look like if it's floating around the flask? As soon as it's formed, This does not look like the carboxylic acid. It looks like what? Acid base. Exactly. It's a carboxylate, which means if it forms in the reaction, you're making this. These protons just went from maybe here, 25, to here, like a million. Well, not a million, but a lot, right? It's now a negatively charged species. Yanking off those protons of a carboxylate, already anionic, you're not going to be able to do it. LDA probably wouldn't be able to even pull that off too. So it's not a million, it's just ridiculously high. So what we're doing effectively is we're protecting the alpha center as the reaction happens. That's why you're just getting simple saponification, no aldol, no enolate chemistries happening under this. You need a different base to make that work. So that's what we're going to talk through today, is we're going to talk about the intramolecular aldols one last time, and we're introducing what's called a Claisen condensation. This is just aldols with esters. And we have two other named ones too. We have the Dieckmann condensation. It's just an intramolecular version of the Claisen, and then the Malonic ester synthesis for what we're doing now. So we ended off on this last time. We talked about, remember in the try it later, we gave you some examples of if you have molecules where both the nucleophile and electrophile, donor acceptor, are in the same molecule. This is an intramolecular aldol reaction. Now normally, we can select. If I take a molecule that has two carbonyls, you have two really easy ways to help you with control. One, aldehydes are generally the acceptors. So if you have a molecule that's both a ketone and an aldehyde in the same molecule, the ketone is usually the donor, the aldehyde is usually the acceptor. That'll go, and that's just based on electrophilicity. That's not the case here. They're both aldehydes. So we can't say one is definitely donor, one is definitely acceptor. So that's our first in terms of reactivity. Second, ring size. I'm trying to form 5- and 6-membered rings. So depending on the position of those carbonyls, generally we can select and say only one product will form, because a 5-membered ring would form selectively versus a 7, versus an 8, versus the bridging sort of structures. So these are just phenomenons that can happen based on the starting material. This is the last class of reaction you could have. You have two carbonyls. They both could be donor or acceptor. And worse yet, both pairings leads to 5-membered rings. This is one where you have no control. This is ideally try not to do this kind of reaction because we don't have any of the mechanisms we could use. If I was to deprotonate there, so let's say that's my nucleophilic center, that would be 1, 2, 3, 4, 5. That would correspond to which of these two, left or right, this or this. If I deprotonate at 1 and then do a cyclization from one to the other carbonyl, which one do I make, left or right? Take a second. Again, just take a second. If you can do this one, that's going to be really good. The other one would be I deprotonate, whoops. If I deprotonate here, this is 1, 2, 3, 4, 5. So you could deprotonate via the red pathway and cyclize between 1 and 5, or deprotonate via the blue pathway, 1 and 5. All right, I want to vote. Number 1 or number 2? Which one of these came from the red pathway? Number 1 or number 2? Hands up. Yeah, it's number 1. Good job. Reason why, remember, if we deprotonate from number 1, this piece is outside of the ring. The ring is joining between these centers. So that's the aldehyde outside. Cool. That means this would be carbon 1, carbon 2, 3, 4, and 5. Remember, you're making a new bond, double bond, between carbons 1 and 5. Most importantly, the O-methyl group is on carbon 2, which means if we go the other way, that would be 1, 2, 3, 4, and 5. New bond between 1 and 5. This is on carbon number 3. That's the blue pathway over here. So this is something, again, practice this point out. This is about locating your product between the two and doing that decomposition. The other way you might be able to do this is, given those two products, hydrate them, and then fragment them, just like we did at the beginning of class. Break it back into the aldehyde starting material. You might be able to see them. But this is a case where if I had that as a starting material, I'm getting both of these two products. I have no control. There's nothing I can do. Remember, when you're doing intramolecular reactions, you're trying to either bias it based on which groups you have. I want ketones to attack aldehydes. Or I'm trying to bias it based, but trying to make one ring size and not another. I'm trying to make a 5 or trying to make a 6 and not these other ones here. This is a case where, I'm sorry, you picked the wrong starting material. You're going to get both. So next one is the Claisen condensation. Now again, this is just a name. This is whoever's doing the study found this reactivity, named it after themselves. People are weird. But conceptually, this is just an aldol, right? So step back and look at this. You're starting with one molecule. You've got 2 of them, so it's a dimerization. Notice now that we are using sodium ethoxide in ethanol and then a water workup in the second step. Now, there's a couple key features of this. Is one, we're using a weak base. We're not using sodium hydroxide. We're using sodium ethoxide. We're doing it in ethanol. The reason for that is right here. Look at the alcohol fragment in your ester. Remember, when we started the class today, we said, well, if I have hydroxide, hydroxide could attack the ester. That's going to kick out the alcohol. Now what I've got is a hydroxide there, not an ester. If, like, that reactions can still happen. I can still get nucleophilic substitution. But if I'm going in with an ethoxide base in ethanol with an ethanol fragment, that can be happening on its own and has no consequence. Even if the ethoxide attacked that center, all you get back is the ethyl ester. We're just spinning our wheels, right? That's just, we use this strategically because it's an easy base to use, the sodium ethoxide. It just means that I don't have this consequence of losing my product to something that's not my ethyl starting material. So my ethyl ester is a good one to use on that. What I'm doing here is I am taking a nucleophilic center with 2 protons, and I'm going to deprotonate it to make the enolate. Now, like we mentioned, the pKa is not super in favor. I'm not going to get a lot of this material, but I can make this nucleophile. Once I have this one, I have a second molecule, the not deprotonated material, just my ethyl ester. Now, if I'm mapping this out to my product here, this is my nucleophilic center. This is my electrophilic center. It's still the same thing. Carbon anion for my enolate is going to be attacking my carbonyl, the electrophilic part. So my donor is in pink. My acceptor is in blue. And if you look at your structures, your donor is actually right here, where that is my nucleophilic center, alpha to the carbonyl that's still remaining. When I make my enolate will be the enolate of this ester. The carbon alpha to that's the one that's attacking. It means that the ester is still part of my, my donor fragment. So this fragment over here, including all this, that's my donor. My acceptor is this center here. This is the rest of that fragment across that. That's from this piece. Now notice what we've done is we've lost this piece. Unlike in the aldol reaction, when we're attacking that lower oxidation state, we're adding to an aldehyde that gives you an alcohol that then reduces, or we actually eliminate it to give you a double bond. Here we're one oxidation state higher. We're at the ester oxidation state. So I'm losing this fragment because my carbon is going to substitute. You go around the carbonyl Tai Chi kind of move, right? Up, down, and out, and you kick out the ethoxide. That's still making this as my new bond between the two. Now, a really important part of this reaction, look at your product. We have a proton in between these guys. What is the pKa here versus here? Starting material versus product. Which one is more acidic? Which of those alpha protons is more acidic? Starting material or product? Product. Why? You've got 2 carbonyls. You've made that center far more acidic. So under these reaction conditions, but until you do this workup, it will actually be chilling out probably like this. Remember, it's a resonance structure, so we've got this delocalized anion between the other points. So that's good because it protects it. Nothing else can happen because it's going to be deprotonated. On workup, we're giving it back its proton. We get the structure you see up on top. That enolate, most importantly, this is still an enolate right here. That's still an enolate. We can do things with that enolate. We'll show you at the end of class. This is actually the core part of what we call the malonate ester synthesis. Most importantly, this enolate has 1, 2 carbons attached to it. We can't add another carbonyl. This is nucleophilic, but the only move I can ever do with an enolate that looks like this, where I have these 2 substitutions, is alkylation. I can add an alkyl iodide, an alkyl bromide. I cannot take this guy and find another one of these guys and say, well, I'm just going to add another carbonyl. I'll do another aldol-like one. It's too sterically encumbered. So that's one of the other reasons we get control of this type reaction. It's only this acid-base addition. It's only this nucleophile adding to give you this compound, which then, because that center is more acidic, it's going to be locked in as this stabilized enolate. And again, most important for conditions, aldehyde, your ester fragment here should match the base and solvent you choose to use to prevent sort of scrambling. So yeah, mechanism of how this actually looks. Step 1, bloop, bloop, bloop. Then we have our second molecule undeprotonated. We're going to do our nucleophilic center tacking to our electrophilic center to make our new carbon-carbon bond. The intermediate we're generating there is going to have our new bond. And because we attacked a carbonyl, like an ester, with a nucleophile and ionic, we're going to have a tetrahedral intermediate left over. And it's 1, 2, 3, 4, which is 1, 2, 3, 4 carbons. That's the first intermediate we generated, and this is the same thing as adding a Grignard to a ester. We're adding other carbon nucleophiles to this ester. Goes into the carbonyl, punches it up, you make an oxyanion, which then, next step, again, this is your carbonyl tai chi, we're going to bring this down and we're going to boot this guy out. So our donor, still here. We have our new bond between the two. And then we have regenerated our carbonyl. And we have the rest of the fragment. 1, 2, 3, 1, 2, 3, 4, like that. And we've made O-ethyl as our negative charge. And like we said, as soon as I do this, that proton is now in range. An acid-base reaction to kind of lock this in as the enolate structure is favorable. So I'm going to copy this. We'll take that to the next page. So here's our fragment. That will give us regenerating this enolate. And now again, this enolate, because it's di-substituted, it's not going to be nucleophilic. We're not adding any more carbonyls to it. But it protects it. We're not going to do anything else to it. There's no more saponification that's possible. It's anion charged. It's basically sitting there waiting until this end of the reaction. What it also means, though, is you're consuming one equivalent of base as this reaction runs. This is something where stoichiometric base is going to be necessary because as the reaction's running, you have to have this extra ethoxide to soak up this proton as the reaction runs through. Last step is on workup, where we're adding our H3O+, we're going to get our final product. We're just adding back that proton. 1, 2, 3. So this is really the aldol reaction. It's similar to nucleophilic acyl substitution. We're just taking the nucleophile, in this case the enolate we're generating from the ester, and we're adding it to another ester.
I don't know if this is a big concern, but since one of the products is FOH, and we're already drowning in FOH, wouldn't that drive the reaction backwards?
Which way, sorry?
Like, one of the products,
Oh, like you're making one equivalent of ethanol, right?
yes,
So doesn't this push the reaction backwards, is what you mean?
because that's our solvent.
No, true, absolutely. Now, but again, looking energetically, we're starting off with FOET minus, very basic. As I run the reaction, I'm making a much more stabilized anion. I'm making a resonant stabilized anion where I'm actually between these two bridging centers. So this is thermodynamically driven in that case by making stability. If I'm starting with OET minus to make an enolate, that ester enolate is less stable than this enolate I made here that's been stabilized by the two. You're right, so it's not fully reversible under these conditions. This is being done mainly because of stability between your less stable OET minus and your basically the enolate that you generate from that one, but good call. So this is your good copy of your overall process as you move it through. Claisen donor acceptor, the naming we have here still follows the same convention we talked about before. The donor is the nucleophile, we're enolate that we're generating. The acceptor is our other point. The only thing that we're adding now is this name. The name Claisen just means we're doing enolate chemistry or an aldol reaction at this higher oxidation state. Yeah? Exactly. If you went in for whatever reason, and let's say I ran it with methoxide and methanol, for example, then yeah, your starting material would probably do a transesterification, and then it will still do the chemistry. In the end, your final product here, where we've got this ester here, will be susceptible to having that exchange. So you'd have more than one product because that OET is going to undergo, some of it will undergo nucleophilic substitution. So the guidance here is don't do that, otherwise you're going to end up with this as a consequence. Make sense? But you're right, that is possible. They're going to happen on competitive rates to each other. Okay, so A, B, C, or D. If you wanted to do a Claisen condensation with this molecule, who's your base? Discuss it between you guys. This should be something where by elimination you can knock off a couple chances. Okay. In one big creepy voice. A, B, C, D, or E? Your answer is B. Okay. Why can I eliminate A? You can go through progressively and knock out each of these points. A is bad because saponification. Yeah. We told you that's going to make a carboxylic acid. Don't do it. Okay, why is this one bad? We just talked about that. That's going to give you, yeah, you're going to make ethyl ester at the same time. It'll work. You're just getting a different product, right? You will swap that to a different group, and then it will transfer. So that's bad. Why does this one not work? What is the pK of acetic acid? Carboxylic acids are 5. That means the conjugate base of something with a pK of 5, strong base, weak base, pretty weak. Remember, what's the pK I'm trying to deprotonate here? These guys are sitting in and around 25. I can't take a base that from 5, like an acid-base equilibrium of 5, to deprotonate something 25. 15, 18 to 25, I got a chance. Some will deprotonate. 5 to 25, man, you are on something. No, there's nothing. That is far too weak. That's not basic enough. Why don't I choose this one? Yeah, same problem, Well, first of all, again, what is wrong with you? This is terrible. This is so scary. Negatively charged nitrogen species should be avoided unless you really need them. But it's the same problem as you have over here. This is like having NH2 minus. Well, that's an awesome nucleophilic acyl substitution. It'll displace in the same way. If you have a negatively charged good nucleophilic acyl substitution as a consequence, or may happen at the same time. It's going to make an amide over there instead too. That'll just scramble up your product. I'm not saying you couldn't do partly a Claisen, but your product definitely would also then scramble as well. So next up is the idea of cross Claisens. The same way we have cross aldols, we can take two different species where we have an obligate donor and obligate acceptor. I can make a product like this because what I'm doing here, instead of saying I'm just doing a dimerization, this is my donor, which is my donor fragment here. That means my acceptor is this piece here to make that part. I would then designate this as my leaving group, right? That's the fragment that's being lost from this reaction. It's not in the actual product. And most importantly, you're doing it with a base that matches the ester fragments from both your two pieces. Once again, I'm using methoxide base for methyl esters, so I'm trying to minimize any nucleophilic acyl scrambling that happening over this. The nice thing about this pairing too is if we do a reaction as designated here, notice this guy here, this acceptor, cannot form enolates. Once again, I'm taking a carbonyl center that is going to act only as an electrophile because I have no alpha protons on the other side of it. It's never going to have a problem where who's my donor, who's my acceptor is going to be ambiguous. So a product or reaction like this can be very useful, but once again, we're following the same rules we talked about for aldols. If you want a cross aldol or cross Claisen to work, you need to plan out your chemistry properly so that one guy is going to act exclusively as your donor, one is your acceptor. The best thing you can do is choose your reagents carefully so that you get the right one. All I mean is that you don't want to sort of fragment a different bond. This is the one that we're forming across here by that sort of nucleophile-electrophile pairing. So the other obligate acceptors we get look like this. These are all Claisen acceptors that all they are is acceptors. They're all going to have an ester fragment baked into them, right? Some kind of an ester fragment in the middle. These are weirder, these carbonates. So they all have some ester. That ester fragment is going to give you both the electrophilic carbonyl, right, and the leaving group. You're going to lose the alcohol part of it. So they're set up to have the electrophilic carbonyl and then some fragment, an O-alkyl part that's going to be kicked off from this group. Each of the four compounds over here, notice that these are set up so that they pretty much do not have any alpha protons. Here, 0 alpha protons. There's not even an alpha center. This is fully substituted. This one's special. What's going on here? Does that one have an alpha proton? It's got one. Okay, so I can deprotonate it. But can that enolate, the enolate you generate from this guy over here, would look like RRO ethyl. Can that enolate do a Claisen reaction? What's the substitution pattern in the alpha center? How many carbons on the nucleophilic center? There are 2. If it's disubstituted, it cannot attack. It can alkylate. I can add an alkyl halide to this. It cannot act as a nucleophile. Oops. It cannot act as a nucleophile to your other chemistry. So it might form, but it's not going to act as a potential donor. It's going to float around in solution, just basically eat up some of your base. The other ones, these are useful because these are the first versions of that same pairing I just designated, except now here you're transferring this whole group onto some center, or you're transferring this whole group onto some center, where the leaving group portion is still this green fragment here. These are higher oxidation compounds. The carbonate is one more oxidation state up. It will leave behind an ester instead of a ketone. And the oxalate gives you this carbonyl sort of fragment. Again, the thing that's important about these points is locate that core fragment. You're looking for a carbonyl with your leaving group. That's going to be your ester, your Claisen transfer, your Claisen acceptor piece. So we'll go through this point in the after class ones too. The last reaction, we're going to talk about this, like in the same pattern through. Remember, we had aldol, condensation. Then we had cross aldol, so this is the obligate donor acceptor. And your final aldol, we called this cyclization, the intramolecular aldol. That's just where the donor and acceptor are part of the same molecule. Claisen has those same three levels. You have your normal dimerization Claisen, that's A with A. Then you have your cross, A with B. We have to do those 2 points. This is the same rule, except now you've got, instead of a ketone-ketone or a ketone-aldehyde, you have an ester-ester. There are 2 esters in the molecule, so you have both. Your donor and acceptor pieces are part of the same structure in order to make rings. It's the same general concept. So in a molecule like this, one of these sides, I'm going to say this one is going to be my enolate, so that's my donor, and I'm going to call that carbon number 1, which means I'm going to attack this carbon, my acceptor, and that is 1, 2, 3, 4, 5 carbons away. I'm making a new bond between carbon number 1 and carbonyl at carbon 5. So mapping that over onto our products, that's my nucleophilic center. It's attached to whatever fragment's outside the ring. I'm going to have the new bond between 1, 2, 3, 4, and my electrophile. The center here, this is number 5. My new bond exists between carbon 1 and carbon 5. And the same rules we talked about before apply. You're looking for 5s and 6s. 5-membered ring and 6-membered ring is what's going to form into these conditions. So let's work this out. If this is your material and you're going to run a reaction, what is your product? This is a case where both the nucleophile and electrophile are in the same molecule. This is a Dieckmann condensation or an intramolecular Claisen reaction. So take a second, try to identify those fragments. Who's going to be your nucleophile, electrophile? How are you going to link it together? What's your ring size? Okay, let's break this out. Again, nice thing about a molecule like this, it is symmetric. It doesn't matter which side you start on. You're going to have roughly the same sort of geometry. So first off, I need an alpha center to one of my groups. I'm going to start and say the one on the right is going to be where I will deprotonate. That will be my nucleophilic center, which means the electrophilic center is the other carbonyl. And if we count that off, that is 1, 2, 3, 4, 5, and 6 carbons away, right? So we're making a 6-membered ring. So if I'm drawing this as a product, oh, one more quick check. Sodium ethoxide, ethyl group over here. That's good. We're setting up with the right base that matches the right alkyl fragment that we're using here. There's no weird transesterification that's happening also. Okay, if I bring those two pieces together, I'm going to make a 6-membered ring. So I'm going to draw this out where I'm going to put the nitrogen on the bottom. And something like this, right? This is the kind of the geometry that I'm building out here. And if I number these out, I'm saying, okay, let's say this is number 3, 2, and 1. So this is my carbon number 1. That is my nucleophilic center. Counting the other way, 4, 5, and 6. This is my electrophilic center. My new bond is this guy right here between 1 and 6. That's the thing that cyclized together. Okay, attaching to carbon number 1, this stays outside the ring. We didn't do anything to that fragment, so that's going to still remain. The enolate that we generate is just coming along for the ride. Carbon 6, though, used to be an ester. It will be attacked. Negative charge goes up, negative charge comes down, and you blow out the O-ethyl. You leave behind a carbonyl. So carbon 6 on the other side of that condensation will be this carbonyl part. There's your product, right? Under acidic conditions, one thing else that you might do, if I work this up under strongly acidic conditions, that's what protonates this center again over here. You might also want to draw this as, well, after workup, it'll be protonated over there too. That's some comment that you might see with these ones, but functionally what we're trying to get to is we're quenching out the enolate charge. We're getting back to a neutral molecule. This was to form the six-membered ring into this part. Make sense? Okay. This is another one. Same practice. I want you guys to go through this, see if you can do that mapping as you make out these centers. So now we have ways of generating these alpha, beta carbonyl systems. We've got these two carbonyls I can fuse. So esters plus another ester gives me what we call these beta keto esters. These are super, super useful because they fit in with another reaction we've done before. This step right here is what? If I take a beta keto acid plus heat under acidic conditions, that's called what? Decarboxylation. I can lose CO2 where over here used to sneaky be this acid, and that's super cool because that acid is really easy to generate. That's saponification. The reason we use this chemistry is because I can take what normally would have been an ester. I can temporarily acidify these protons because now they're sitting between two carbonyls. I can do normal chemistry of those two carbonyls, and then I can blow off that ester, the acid function. This whole piece right here is going to be deleted to give me back just a ketone. This is just like what we did with the Gabriel synthesis. Remember, if I was doing Gabriel synthesis, I'm trying to get a nitrogen minus. That's not easy to do, so what I do is temporarily make it more acidic by putting other carbonyls next to it to stabilize this group. We're doing the same functional thing here is I'm converting one of these centers to these dicarbonyls to make the CH2 in between it a nice, normal, easy to use enolate. I can use very simple bases like methoxide and ethoxide to do this deprotonation. But it comes to the consequence where after I've done my chemistry, I need to delete that CO2, but it becomes like a protection group type part. So we have two general ways that this looks like. This is what we call malonic ester or malonic acid kind of synthesis. So we can have diethyl malonate, that's the name of this molecule. It just has esters on both sides, but notice in the middle, we've got our nice superacidic protons in between. The acetoacetate, that's this one, same thing. I have two acidic protons in between. This is where I'm targeting my enolate in both cases. It's in between those two. Nice thing about the ethyl acetoacetate, I have alpha centers on the other side, outside the carbonyl, right? These are also alpha centers, but I'm not going to deprotonate there. They are way, way, way less acidic, so I can target where I want this reaction to happen. Both of these two fragments, you would use them, you make the enolate, you do your addition, you do your chemistry, and then you saponify the acid and decarboxylate it to delete it out to actually make a more compact structure. So the good news is, again, this is a really easy way to do the effective chemistry. The downside is you've blown off a part of the molecule, so this becomes harder for synthesis. It's harder to see a part of the molecule that you don't see anymore, right? It's been deleted from that fragment. It was part of the intermediates. You have to invoke it for making the chemistry, but then you're removing it in your final product. It's what we call a traceless reaction. Because it's difficult to see it was even there, you have to stick it back in intentionally. All right, that's basically what you want to look at like this point. The bottom reaction, it's those red carbons that get transferred to your real target. In the other one, acetyl acetate, it's that acetone structure that gets transferred to your real product. The gray stuff could be lost in the context of the reaction. All of this is saponification, decarboxylation. This gets lost by saponification. This gets lost by saponification, decarboxylation. So this is the echo of the part of the molecule that used to be there that we've now hydrolyzed off. And again, the analogy is really Gabriel synthesis. This is where we took a whole bunch of other carbons to change or modify the reactivity of a nitrogen to make it more acidic, easier to handle. And then when we're done, after I've done a nice SN2 chemistry in the Gabriel synthesis, I then strip off that phthalimide. This is the same thing here, where I'm taking what would have been normally a really difficult enolate and making it much more well-behaved. Eventually, then I have to follow up these other steps. So this is, again, why I love organic chemistry is it's exactly like life. There's this direct way to do it, but it's going to be hard and painful. There's this indirect way. You have to pay with more time, but it's way more controlled. Everything is about zero sum. Everything is about the pie does not grow, and you just have to give and take between two different sides. So this is generally how this transformation ends up looking. You end up starting off with these diethyl malonates. You carry out chemistry to install a group. If you look at this, what we're doing here, first step, I am making my enolate. So what I will generate from there is going to look something like this. Now, I add a alkyl halide. I'm doing simple nucleophilic addition. That's going to add my second step. I can alkylate my enolate, where I'm installing this R group. The nice thing about these chemistries is I can do the deprotonation, I make the enolate, I then surgically install my R group, and if I want, I'm done. I've installed my R group, I'm finished with it. These next two steps, heat and acid, we're going to do saponification, decarboxylation in two different steps to give us back here. Remember, this is like we had eventually. There used to be a ghost ester chilling out over here. That's very badly done. Ooh, boo. And this used to be an O-ethyl as well. That's the piece that got reduced down in that third step. But this sequence we use to actually progressively and target how we do these installations. Okay. That's all we're going to talk about today. I'll see you guys on Friday. Okay, for our problems, we're asked to draw the crossed Claisen product from this. Now, we're giving a reaction where our base is sodium methoxide. Now notice both of the esters are methyl esters, so that's compatible. That makes sense. We have to identify which is the donor, the nucleophile, and which is the acceptor. And it turns out that this one has protons on the alpha center. This does not. So there's no way that that first molecule is going to be your donor. That's going to be an obligate acceptor. So this one here is going to turn into our enolate, and then that will then add to our other fragment. The intermediate we're generating there is our tetrahedral intermediate we've drawn a couple times before. And let me just move this up. Oops. Too many pieces. Sorry. So it's 1, 2, 3, 4, 1, 2, 3. Too many. There you go. That's the addition. We've got a new addition to a tetrahedral intermediate like this, which is going to then collapse and kick out that other fragment. So the final product we're going to generate will be the aldehyde, in this case, added to this center. So we're again just mapping out the carbons. Electrophilic carbon there is this one here. Nucleophilic carbon is this one here. Oops, there we go. There we go. Yep, looks good. And our final product just looks like that, where we've formed this bond in between the two. Okay, for this question, we're asked to find the major organic product for this Dieckmann condensation. Remember, this is an intramolecular Claisen. We're using sodium methoxide as a base. Note that we have the ethyl ester in both of these cases too. And it happens that even though it may not look quite like it, this molecule once again is symmetric. So we have protons here as our alpha center, and just based on the symmetry of the molecule, these here are identical. So you're going to deprotonate one of them, and so for now, let me say I'm going to assume this is going to be my nucleophilic center, that's my donor, and then my acceptor would be this center here. Because of that, we're going to have a 1, 2, 3, 4, 5-membered ring. So we would be building a 5-membered ring attached to the benzene. So that's the back benzene core. We've got a 5-membered ring that we're building off of that like this. On carbon number 1, we're going to have the ethyl ester still in place. And that means carbon number 5, again 1, 2, 3, 4, and carbon 5 here, that's going to be a carbonyl. So as I mentioned in class today, we're using the malonic ester synthesis to start off with this molecule. We're acidifying these 2 protons, and we're using this chain sequence here to form the enolate, add an alkyl group, and this last one, this is our close, which actually decarboxylates it. So using that same sort of strategy, we can actually use this to add 2 different alkyl groups in a surgical fashion. So step 1 here, we're using our base. That's going to deprotonate this middle compound. So after step 1, we're going to have our ethyl as our enolate, like this. Next, step 2, we're adding this RX, call that some type of like alkyl bromide or alkyl iodide. So what that's going to do is, this is my electrophile. That makes my nucleophile, this compound here. That's our enolate. So after that first addition, we're going to have back to our 1,3-diketone. All we've now done is install one R group at this position, and we still have a remaining proton left. We can treat it with another equivalent of base. So after step 3 now, what we're doing is we're converting it back into an enolate again. We're making it back into a nucleophile. And remember, this alkylation step only works on centers that we have these kind of doubly substituted enolates. So after this first addition here, we have now made a doubly substituted enolate. This nucleophile will only allow something like this alkylation again. So now we're going to do step 4. Step 4 is going to come through, and we're back to another alpha beta unsaturated system. And we have now 2 different groups attaching here, where we've attached them sequentially, 1 and 2. There's no control of the stereochemistry. It will be racemic, but it allows us to surgically add, first of all, enolate, first addition, enolate, second addition. Now we have both substituted. We can then finish it off in our final step. This is step 5 here, where we are doing the saponification, cutting it back to the carboxylic acid, and then with heat we're doing the decarboxylation. So that's going to get us to this final component here, where the embedded molecule has now lost one of these things as our CO2. We've lost the ester groups on both sides to give our final compound. So applying that to the same strategy here, we can start with this malonic ester. We're going to treat with ethanol and base, and if you notice, we have our 2 protons here. This sequential addition will do enolate generation, first alkylation, enolate generation, second alkylation, and then a decarboxylation. So showing that out, I'm going to show the compound just before, after each one of these steps. So once again, step 1, we're going to have our enolate. Step 2, we now have, let's just make it colored. Our ethyl bromide. So we've added the first equivalent to this. Step 3, we're going to add another equivalent of base. So we're going to make another enolate again. the alkyl group is still attached. Now, step 4, we're adding the second equivalent to this. And notice here we have these 2 carbons, so it's attached. 2 carbons, 1, 2, and the aromatic group like this. And then in our final step is the decarboxylation, so step 5. We will be losing one of these CO2 groups, and it's ethyl and saponifying over here. So that gives us a carboxylic acid on one side to our middle carbon. So that middle carbon here is this middle carbon here. And then we're going to have an ethyl, and we're going to have like this. I think that's right. So 1, 2 carbons is 1, 2 carbons. Yep, that looks good. And again, we'll have both enantiomers of this molecule.